Hello everyone, this is Dr. Lennon, and today we're going to talk about solving inequalities. So inequalities are things that talk about comparing x to other quantities or expressions to other quantities, and kind of the fundamental rules of solving equations apply to them with kind of one adjustment. So let's kind of look at what can we do to solve inequalities. Okay, so kind of properties, let's call them. So what we can do is we can add or subtract the same number to both parts of the inequality. We could multiply or divide by the same positive number . And the third thing is, if we want to multiply or divide by a negative, then we have to flip the direction of all inequality symbols. So this is the thing that makes it a little bit different than equations. So if we multiply or divide by a negative, we must flip the direction of all inequality symbols. So you might ask, well, why is that the case? Let's just try to think about a very concrete example. This is just to highlight why property 3 is true. So let's just consider, let's say x greater than, I don't know, 5. So if you have x greater than 5, those are all the values that are bigger than 5. So if you have 0 here and say 5 here, it's all the numbers not including 5 that are bigger. So all the numbers kind of shaded in this direction. So that would be the graph of the solution set. Now what if we tried to solve, let's say, negative x less than negative 5. Well, there's two ways to do it. We could use property 3. Property 3 says if we divide by negative 1 on both sides, we get the correct thing, so we're going to get the same thing as above, but we have to flip the direction of the inequality symbol. So it was negative x less than negative 5, and it becomes x greater than 5. So we flip because we multiply by negative 1. Or we divide by negative 1. Multiplication and division by negative 1 is the same thing. But alternatively, you could solve this just using addition to show that we get the same result. Alternatively, this problem could be solved in 2 steps with addition. So how would you do that? Well, you would just add x to both sides and also add 5 to both sides. So if we had negative x less than negative 5, let's start by adding our x plus x to both sides, which is valid because we're just adding a number to both sides. So then we would end up with 0 less than x minus 5. And then to move the 5 to the other side, we add 5 as well, and we end up with 5 less than x. And notice that's the same thing. So which represents the same interval as x greater than 5. So even though it looks a bit different, the inequality symbols are not reflexive, as is the case for the equations that we've seen so far. Okay, that's pretty much it. That's why that's true. Let's just jump into solving some of the easier ones, and we'll just graph the solution sets. So, example, solve each inequality. And graph the solution set. So let's start with something relatively simple, 5x greater than or equal to 15. So what you typically want to do, the same thing as an equation, you want to isolate the variable part and then just multiply or divide once you're there to isolate x. So in this case, x is being multiplied by 5, so we want to divide both sides by 5. No need to flip because that's a positive number, so we get x greater than or equal to 3. And so let me add, I said and graph already. So in this case, the x's are bigger than 3, so the part of the solution we want to shade is all the numbers larger than 3. So, 0 might be in the middle, 3 would be over here. I like to do it above the graph. Some people do it right on the graph, but when you include the number, in this case we're including 3, we're going to shade the 3. If it were, say, strictly greater than, we would have an open dot on the 3 rather than a closed dot. Okay, so let's look at B. Let's say we have 3x minus 2 less than 10. So this is a two-step problem because we want to add 2. And then from there, we're also going to, so then we've isolated the 3x. So 3x is less than 12. And then we want to divide by 3. So we end up with our answer of x less than 4. So, again, you might have 0 here and 4 over here. This time it's strictly less, so our answers are the numbers less than 4, but we're not including 4. It's just a boundary value. We don't include it, and we want to shade to the left. So this is our solution set. I mean, I could use a different color to shade it, but you get the idea. We'll learn in the near future about something called interval notation, which is another way to write these sets of numbers as opposed to the solve inequality or the graphed solution. Okay, let's look at another part C here. So let's say we have 2x plus 14 less than 6. Again, this is another two-step problem. We just want to begin by isolating the 2x, and we can do that by subtracting 14 on both sides. So we end up with 2x less than negative 8. And again, we're dividing by positive 2 here, so there's no need to flip any symbol. We end up with x less than negative 4. Again, that doesn't have the equal bar underneath that inequality symbol, so that is an alert to us that we're going to have an open dot in our graph. So if we call this 0, negative 4 is going to be somewhere over here, and the numbers smaller than negative 4 are going to be to the left. So that's the convention, smaller numbers to the left, larger numbers to the right. Okay, D. So you can have ones that have maybe a couple more steps. Maybe you have some numbers to collect on either side, but it doesn't really matter. And if you're kind of careful, a lot of times with these, you can avoid the problem of flipping if you just make sure that you're collecting the x's so that the coefficient is positive. For instance, to collect the x's, there's two options here. You could either subtract 4x from both sides, which would move the x's to the right, or you could add 2x to both sides, which would move your x's to the left. Now, if I add, then I'm not going to end up with a negative coefficient in this example, so I'm going to choose to do that. I'll begin by just adding 2x and combining my like terms that way. So I have 2 plus 6x less than or equal to 6. And then I just need to subtract 2 to move my standard numbers to the right. So I have 6x less than or equal to 4. And then I can divide by 6. And so I have x is less than or equal to 4 over 6 is the same thing as 2/3. So again, that is our answer here. So shading that, we're going to end up with, 0 here, 2/3 somewhere to the right of it. and then we're going to be a shaded dot, and bigger numbers are to the right. Sorry, we're less than or equal to 2/3, so we want to be shading to the right. So let's go ahead and do that. So smaller numbers are to the left. The values that are part of the solution set are numbers that make sense for x, so the numbers less than 2/3 would be to the left. Okay, let's do one more of these. Say e, let's say we have 9 minus 3x less than or equal to 6 minus 9x. Again, if you're careful about which way you move the x's, you can avoid the problem of needing to flip the inequality symbol. So if you would add 3x, you would end up with negative 6x on the right. Whereas if you add 9x to both sides, you end up with positive 6x on the left. So we'll add the 9x to both sides, and that should avoid the problem of flipping the inequality symbol. So we have 9 less than or equal to 6. Excuse me. The negative 3x plus 9x is going to leave us with plus 6x on the left-hand side. So this is less than or equal to 6. And then we want to subtract 9. So we have 6x less than or equal to negative 3. And we want to divide by 6 on both sides. So we have x less than or equal to negative 1/2. And again, those are going to be the numbers smaller than or equal to negative 1/2. So if you have 0, negative 1/2 is to the left. And you're going to shade that dot and shade to the left. Okay, let's look at some compound inequalities now. So compound inequalities mean you're looking for numbers between two boundary values, a lower bound and an upper bound. So the only difference here is you're going to kind of have 3 parts. So anything you do to one part of the inequality, you're going to want to do to all 3 parts. So in this example, we have the 3x plus the 8 in the middle. That's what we're focused on. We want to isolate the 3x to start. So we can do that by subtracting 8. So we have minus 8, and minus 8 to all 3 parts. So we have negative 13 is less than or equal to 3x is less than, I don't know, maybe it's easier to work with fractions here, maybe not. We could say minus 8.5, which would be minus 17/2, or we could just go with a decimal. This would be minus 7.5. You could do it either way. So now we want to divide by 3, and again we're dividing by a positive number, so we don't have to worry about flipping. So we get negative 13 over 3 less than or equal to x less than, this is negative 2.5, which you could also represent as 5 over 2 if you want to do it as a fraction. But I don't mind if you use both here. So notice this time we have our 2 boundary points, negative 13 over 3, and we have negative 2.5. So we would have a shaded dot because we have the less than or equal with the negative 13 over 3, and we'd have an open dot on the negative 2.5, and the values in our solution set are just the values in between those 2 dots. Again, the shaded dot is including the number, and the open dot does not include the number. It just represents like a boundary. Okay, one more of these. So sometimes a helpful hint, if you have some fractions, you can start by multiplying everybody by a common denominator so that you don't have fractions until the final step. So this case is a prime example. If we multiply all 3 parts by 12, then the fractions will disappear temporarily. So we'll do that, multiply all 3 parts by 12. So 12 times a half greater than or equal to 2x minus 5 over 12. This will also be multiplied by 12, and then multiply the 1/3 by 12. So what we're doing here is multiplying all parts by 12 to eliminate fractions temporarily. Okay, so now we can simplify. We end up with 6 being greater than or equal to just the 2x minus 5. The denominator of 12 cancels, and then this is greater than 4. And then we can solve in the same way. Before, we want to add 5 to all 3 parts. So we end up with 11 being greater than or equal to the 2x, which is greater than the 9, and then we divide everybody by 2. So we see that 5.5 is greater than or equal to x, which is greater than 4.5. So we can graph that over here. We have the 4.5 and the 5.5, and we know there's an open dot with a 4.5 and a closed dot with a 5.5, and we're going to be shading in the middle. Okay, so let's talk about some quadratic inequalities, or let's say some nonlinear inequalities. All of the previous ones were linear because they just involved solving for x, and we didn't have to worry about x being raised to any powers. So basically the idea is use test value regions. So use test value regions. Because essentially what it boils down to is we know, let's say, a positive times a positive is positive. A negative times a negative is also a positive. And we know that a positive times a negative will come out to a negative. So we can break things up to figure out whether these things are going to happen. So let's look at an example. So let's look at a few examples at least. Let's say solve and graph the solution. So let's say we have something like x times x plus 1 is greater than 0. So what we have here is we have two expressions, x and x plus 1, being multiplied together. And we know that this is going to be a valid solution when it's greater than 0. So the interesting points actually are, we know it would be 0 when x is 0 or when x plus 1 is 0. So we can kind of break up all of our values based on that. So the test value regions we'd be establishing are -1 and 0, right? So this quantity, x times x plus 1, equals 0 when x equals 0 or x plus 1 equals 0. And we know x plus 1 equals 0 when x is -1. So when we're solving an inequality, we're looking for all possible real numbers that would satisfy the initial inequality. So basically, there's 3 regions now that we've divided everything up into. And the regions themselves will either be part of the solution or not part of the solution. And that's what we need to test. So we want to test whether if we plug any number from this region in, what will happen. And the result will be the same for any number that you plug in. So let's say we want to do region 1. Test a number, test any number in region 1. So that basically means you can plug in any number that's less than -1. So let's say -2. We could do -2 times -2 plus 1. I'm just plugging them back into this original inequality, x times x plus 1, but I'm changing x to -2. And this will come out to -2 times -1, which is +2, which I know is bigger than 0. So that means region 1 is part of the solution. So we could put a big check mark next to this if we want. Then we could test region 2, and we'd be doing the same thing. Test any number between -1 and 0. So maybe I'll test -1/2, negative 1/2 times negative 1/2 plus 1, well, that would be negative 1/2 times positive 1/2, which is negative 1/4, which is less than 0. So that does not check out, right? Our solutions to A here are only those values that result in a positive. And then we could also test region 3. So region 3 would be any number bigger than 0. So we could plug in, say, positive 1. So we could do 1 times 1 plus 1. This comes out to 2, which is greater than 0. So again, a check mark by this region. So the solution to the above inequality is all numbers in regions 1 and 2, or regions 1 and 3. Again, if you plug in negative 1 and 0, then that would result in 0, and we need our numbers to be strictly positive. It did not allow for inclusion of 0. So we have our numbers negative 1 and 0, and we are including region 1, so we'd shade region 1, and then we would also shade region 3. So all of those numbers are part of the solution set. So you've just kind of got those two disjoint regions. So we could look at another one as well. Let's say something like x plus 9 times x minus 1. Let's say, I don't know, less than or equal to 0. So what would we do? Well, we know x plus 9. First, we'd want to figure out the places where they equal 0. This is a quadratic that's already factored, so that's pretty easy. It's going to be x equals negative 9 or x equals positive 1, setting each one of those zeros. So then we get our three regions in the same way. We would have our negative 9 and also our positive 1. And two numbers like that will chop the real number line into three regions. So again, you just go through each region testing a number in that region. So let's say negative 10 for the first one. So negative 10 plus 9 times negative 10 minus 1. Well, this would be negative 1 times negative 11, which is positive 11. But that's going to be a no-no because that's a positive number. And this time we're looking for numbers less than or equal to 0. So we want our numbers that are negative to be part of the solution. So that's a no. Region 2, a number between negative 9 and 1. A good number to choose when it's there is always 0. So we could do 0 plus 9 times 0 minus 1. And that would give us 9 times negative 1, which is negative 9. This is less than or equal to 0, so we get a check mark in region 2. And for region 3, we could have, I don't know, let's plug in 2. 2 plus 9 times 2 minus 1. That would be 11 times 1, which comes out to 11. Again, that's a positive number, so that's not part of our solution set. So region 2 is the solution set here. So notice the original expression x plus 9 times x minus 1 less than or equal to 0 allows for things to be equal to 0. So we will include values that are equal to 0 in our solution. So we have negative 9 here, and we also have 1. Both of those numbers will be included because we have the underscored inequality symbol rather than the strict inequality symbol. So all numbers in region 2 and negative 9 and 1 are in the solution set. Let me get rid of that comma. Okay, one last one. This one will also be a nonlinear equality, but it will involve a division. So let's say we have something like x plus 2 times x minus 5 less than or equal to 0. Now, the thing is, So we know that if you plugged in -2, so if x equals -2, then the whole thing, x plus 2 over x minus 5, would equal 0 over -7, which equals 0. However, if x were to equal +5, then what would happen? Our x plus 2 over x minus 5 would equal 7 over 0, which is undefined. So for that reason, when you divide by 0, it's undefined. So 5 will never be a part of any solution set. We see that less than or equal to 0 means if your fraction comes out to 0 here, it is part of the solution set. So we can already see -2 is part of the solution set. This fraction is going to work just like anything, right? If you take two numbers and you're dividing them, it's going to be the same as if you multiply them. So a positive over a positive is positive, a negative over a negative is positive, or any combination of a positive and a negative will come out negative. So we're still going to set up the test value regions as before. So I'm still looking at my numbers here, -2 and 5. And from what we set up here, we already know what the dots are going to look like. I know that I'm going to have an open dot here, and I know 5 is going to get a closed dot. I just need to figure out what's going on in the regions, right? Region 1, region 2, and region 3. So I just need to test those regions. So in region 1, let's plug in, say, -3. We could get -3 plus 2 over -3 minus 5, which comes out to -1 over -8, which is +1/8. We're looking for less than or equal to 0. 1/8 is a positive number, so that's not part of the solution set. Then I could go to region 2, and I can plug in 0. 0 plus 2 over 0 minus 5 comes out to 2. 2 over -5, or -2/5. Which is less than or equal to 0. So this region is part of the solution set, so we know we're going to be able to shade between the dots. And then region 3 is also going to fail. Let's plug in, say, 6. 6 plus 2 over 6 minus 5 comes out to 8 over 1, which is not less than or equal to 0. So that region does not check out as part of the solution. So our solution set is already what we have shaded. So that's it for the basic kind of nonlinear inequalities. If they gave you something that wasn't factored, you might have to actually factor it, but I don't think there's any of those quite yet. So linear equations, that's all you have to remember. Isolate x, then multiply or divide. If you end up multiplying or dividing by a negative, then you need to flip the inequality symbols. A lot of times that can be avoided by just choosing which way we add x, whether we want to move our x's to the left or to the right. So if you do a preliminary investigation and make sure that your coefficient is going to end up as a positive, then you should be okay there. And for these nonlinear inequalities, we're setting up test value regions. So we're moving 0 to one side, and we're getting them either factored or in some type of fraction form. And then we want to find the places that make those factors 0. So that divides up our real number line into some regions, and then we test those regions to see whether or not the original inequality is going to turn out to be either positive or negative. And depending on how the inequality is set up, that will tell us whether or not it's included in our solution or not part of the solution. So that's it for this section. This is Dr. Lennon signing off.